Okay, so second part of the Geotech FE exam in civil engineering is soil hydraulic, and the soil hydraulic portions of in your FE manual is located in page 260, and it just pretty much is just half page of 260 because we start from here. Starting to this part to the end of the page, those are the soil hydraulic portions of the FE exam Geotech part. So let's look at let's go through this just half page and see what we have, what we covered in the FE exams. For soil hydraulics is highly laboratory testing dominant because it has to test for the constant head test and falling head test. So the two tests right there pretty much like come out with a formula. So for the falling head test, which is this formula here, this is the constant head test formula to find the hydraulic conductivities. And the second part is this equations here for the falling head test. Again, is equations to find the hydraulic conductivity K values. So it is essential to understand where the formula come from, and also to help you to solve the FE problems. Is great that you can refresh your studies in geotechnical laboratory testing. So if you go to my YouTube CE 368 playlist, you will find the hydraulic laboratory tests, the one for the falling head and also for the constant head. But anyway, so let's refresh what are the constant head tests first. So I have laboratories set up here to describe the constant head test. So if this is the soil samples that we're testing, so this like a one orange rectangles is our soil specimens inside like a permeator, which allows the water goes in and go out. And this soil specimen, it has an area right there of A, and also it has a length of L right there. So we want to find out the hydraulic conductivities, the K values, which means how easy the water or the hydraulic resistance of the soil when the water pass through. So the concept is again like we want to quantify how easy or how hard the water pass through the soil samples here. So the way that it works is the K parameters is a parameters that we cannot directly measure, but with like a laboratory setup like this, with some like a known quantity that we can measure in the lab, like the two parameters are pretty right there. The areas A of the soil specimens and the length of the soil specimens, those are the physical parameters that actually we can measure, right? If we have a caliber or if we have a straight edge, then we can directly measure the length of the soil specimens. So those are the two parameters that we need. And the overall setup, we call this to be a constant head test, because what we do is we apply water head to our soil specimen. For example, here we connect the water tubes to the pipette here, which also we make sure we have a reservoir of water supplying the water, such that the water level here stay constant. So that's why we call it constant head test, because we have enough water that the water level won't drops. in the lab, it can be done by like a huge water tank, or like constantly you have water coming in, such that again the keys, the water level, we won't change. So the water will go through the pipette and then like connect to the bottom of the soil samples, and you flush through the soils, and then it comes out from the top. And we collect the amount of water that comes out in this graduate cylinder here. When we, again, this is parameters that we can quantify because we can measure the volumes. So we call Q here, which is the water that passed through the soil specimens at a given time. So the Q and T, they come as a pair. If a given amount of time, how much water has been collected. And we also can measure the height or the head of from the water level open to atmospheres to the water comes out from the top again to the atmospheres. So those give us the head that drive the water pass through the hydraulic resistance, which provided by the soil specimens. So with all this like a known parameters, with the help of Darcy law, we hope that we can find the hydraulic conductivities of the soil, which is the main purpose and also part of the FE exams that requires you to understand how to apply this formula right here, which is the content head test formula to find the hydraulic conductivities. So we start from a formula which is the velocity of water, the seepage velocity of water is equals to the hydraulic conductivities times the gradients. So this is our first equations, and you can also actually see these equations again on the FE manuals, which we call the discharge velocity there, the discharge velocity of water coming out from soil. So this is our first formula, and again, Darcy law, Q equal KIA, and we know like KI is can be replaced with the velocity, discharge velocity, so it goes V8. So from this formula here, from the Darcy law, if we multiply both sides by time t, and in fact, what we get like the acute, the full weight times t. So this has unit of m cube per seconds, for examples. And then if we multiply by the seconds there, then which is the time domain, the time dimensions, it can cancel out, and we get back the volumes. And the volumes is like what we can measure in the lab with a graduate cylinder. So with that, we have another formula using the Darcy law. And if we combine equation 1 and equations 2 there, we get this formula. So equation 1 and equation 2, pretty much we substitute the velocity equal KI into equations 2, then we get this formula. And we organize what we find, right? We want to find out the K value, the hydraulic conductivities. And then we get this formula. And I there, as mentioned in the FE manuals, is DH0. And what I is further like also described as the hydraulic gradients, but the FE manual didn't tell you. Like I is the hydraulic gradients, and is equals to THDL. So if we plug it back to the formula, then we get this one. And your FE manual call like the T that collect for the time T corresponding to the amount of volumes, that's T sub E. So this will be the formula that you have in your FE manual. So where this formula come from? It's come from falling head test set up, a constant head test setup in the laboratory. Again, like what we want, the purpose is we want to find hydraulic conductivities, but we cannot measure it directly, but we can find it indirectly through some other parameters that we can physically measure in the lab, including the big QE right there is the water volumes, and DLDT are the gradients, and also the head, the area, and also the time. So this H here, pretty much DH here is pretty much just the head that we apply in the lab. And the next equations I want to go through is the falling head test. So very similar setup, But this time, instead of having a constant head that you have a water reservoir, provided the water table is not changing. Now the pipette, you allow the water to drops. The water level in the pipette allows to drops. So same setup, you have water pipette connections to the bottom of the source specimens, and water travel through the soils samples, and water come out from the top. At this time, you don't need to collect water with a graduate cylinder, but you let the water level drops. So that's what will be the water level before you open the valve. And at that time, so you have a head, initial head right there. We call H1, and then you open the valve, and then you time yourself. And at certain point, so this is at T1, at a certain point, then the water level drops, and then you close the valve, and then you have another head right there. So again, with this measurable and known parameters, we want to find the hydraulic conductivities. And the same thing, we know the area of the source specimens, and also we can physically measure the length right there. So with those measurable parameters, let's see what we can do. So we use the to consider the flow into the soil sample. So the and then also we consider decibel again. We consider the amount of water going into the soil samples through the pipette. So we call the Q in is equals to Ki, the area. And this time the area is the small area of the pipette. So this is area A right there. So the this equals to Ki. If the small a, then we know Ki is equals to discharge velocity. And since this is a decreasing, so we have a negative values right there. So the velocity equals to negative dH dt. So change of the height per time, the change of the head per time. So the Q in with all this, we would put down the equations at negative A times dH dt. So this is my equation 1 for the amount of water that goes in. And for the water that coming out from the soil samples, so the Q out equals to KIA again, and now this A is the capital A here with the area of the pipette, sorry, area of the soil samples, the capital A, so it goes to KI, the K, and the gradients I here is equals to the head delta H divided by the length of the soil samples, the area of the soil samples. So that's just the Q out. And by equilibriums, the amount that of water goes in equals the amount of water that go out. So we can combine equations 1 and 2. And we reorganize the equations. And we integrate with the time frame corresponding to the head water head level. And after we do our integrations, we again, the purpose is we want to represent the K values, the hydraulic conductivities with the known parameters. So now K equals to all these parameters that we can measure in the lab. And this is natural log, and if we convert that back to log base 10, we got this formula. And this formula is what you got from your FE manual right here. So this is how we get to the point we can apply this formula to find our hydraulic conductivities with some known measurements that we can make in the lab, including the area of the soil samples, the small area of the pipette or the tube, the time they take you finish the test at corresponding at different heads, and also the length of the soil columns. Okay, next, we touch base on this, the next formula, the discharge velocity previously. But what is it? Actually, we can visualize with this like a setup here, the laboratory setup. When we have head difference to drive the water pass through, for example, this soil specimen again. And it has a velocity for how fast the discharge, the water discharge from the upstream to downstream, from the higher head to lower head. And this discharge velocity is equals to K times I. So this is the K values. Again, it's representing how easy the water flowing through the soils. And the gradients we get is equals to the delta H divided by L. So delta H is, again, is the head difference. And the L here is the length of the soil specimens. And the velocity is equals to, is proportional to the hydraulic conductivity of the soils and proportional to the head, but inversely proportional to the length of the source column or source specimens. So that's just the discharge velocity, and pretty much you can visualize the concept of the velocity, discharge velocity from this like a simple laboratory setup. And last but not least, on your FE menus, there's some more equations, including effective safety against the seepage liquefactions. So what is soil liquefaction? The soil liquefactions is based on the effective stress concept. So the effective stress of soil equals the total stress minus the pore pressure. So if the pore pressure generated pore pressure is high enough that like at the equal amount of the total stress right there, and the effective stress will become zero because now U is like almost as high as equals to the sigma. So the effective stress could go to zero. And if we lost all the effective stress of the soil, then there's no more strength. And at that time, the sand could behave like liquid. So it's quite like a terrible. And so that's why when you have a loose sand deposit, because of earthquake or because of other dynamic loading like blasting, anyhow, like maybe even like static loading that allows you to generate excess pore pressure. We always need to keep an eye on it, because at that point, if the pore pressure is too high, then liquefactions can happen based on the effective stress concept. So you find the equations here, the effective safety against seepage liquefactions, and which is I sub C divided by I sub E. So I sub C is this equations, the saturated unit weight minus the water unit weight divided by the water unit weight. And I sub E is the seepage exit gradient. So what is exit gradient? Usually, like, you can visualize it or try to understand it through a full net. So when you have a kind of like a geostructure right there, for example, this is a simple dam that I just quickly draw, and with a simple full net underneath it, so you can expect the water pass from the upstream to the downstream, and at this particular full net grid, we can calculate the head difference. So this is an equal potential line. You can calculate the head difference, and then also through the length right here. So the length here gives you the delta L. So with this exiting grid, we can calculate the I sub E equals to the change of the height here divided by the travel distance. So this is the exit gradient. And with that, you know the exit gradient, you know the I sub C, and the factor of safety against seepage liquefactions can be calculated.